All right, today what I'd like to do is I'd like to do the same kind of example we looked at before break, but in the context of using something called the continuous convolution formula, which actually, I mean, the formula itself is difficult to understand, but using it, it's not too hard. And it does simplify the calculation quite a bit. You'll see here. I'll illustrate for you here. So let's think about it in general. We're looking at something called the continuous convolution formula for what? Well, in a special case, for finding the PDF probability density function of the sum of two non-negative continuous random variables. Continuous convolution formula for finding the PDF of the sum of two independent, they do need to be independent, continuous random variables that are also non-negative. I'll say continuous non-negative random variables based on the PDFs of those two continuous non-negative random variables. So let's say we've got two independent random variables, X and Y. They're independent. With PDFs little f sub x of little x and little f sub y of little y. Okay, as we've often done, we'll call the sum of these two random variables W. Maybe it'd make more sense to call it S, but I've been calling it W. Let W equal X plus Y. Question is, what is the PDF of W? Let's derive this in the abstract. Okay, and then we'll apply it to a certain situation. In fact, the same situation we looked at before spring break. We'll use the CDF method. Start with the CDF method. Cumulative distribution function method, where we first write down the CDF of W, and then we differentiate it to find the PDF. Right, as we've done a lot. So capital W is my random variable that is the sum of capital X and capital Y, and it's this letter little w is the variable for the CDF and PDF of capital W. As always, remember this is always true whether your random variable is continuous, discrete, or mixed. The CDF is the probability that the random variable is less than or equal to the given input for this function, little w, as always. The way you compute it then after this point is what changes. Well, what is W? It's X plus Y. How are we going to do this? In general, we would have to use the joint density of X and Y. Right? We need to think multivariable calculus here. Go ahead and draw a picture. Here's your plane. Label this axis X and this one Y. These are non-negative random variables, and it makes it simpler then. We can just focus on the first quadrant. What's W? W is just some non-negative number. Little w is some number greater than or equal to 0. What does it mean for X plus Y to be less than or equal to little w? It means if you draw the line Y equals little w minus X in this plane, it means you're on a point, you're at a point below that line. Right, this line is going to have a y-intercept of w and a slope of -1. There it is right there. The y-intercept is little w. The slope is -1. And therefore, the x-intercept is also little w. For x plus y to be less than or equal to little w means that you are below this line. And we are also in the first quadrant because x and y are non-negative. So we're in this triangle somewhere for this condition to be true. And what this means is to find this probability, you need to do a double integral over this region of the joint density. Double integral of the joint density f sub xy of little x little y. That's the joint density. I haven't said what the joint density is yet, but the independence assumption is going to help us figure that out. This is the joint density, excuse me, of the bivariate random variable xy. I'm not integrating over a rectangle here. I'm integrating over a triangle. Now, again, a few of you probably have not had multivariable calculus. It's okay. I think we can still talk about this. If it were a rectangle where x goes like from a to b and y goes from c to d or something, and if we integrate with respect to, say, y first and then x second, which is the way I usually do it, we'd let x go from a to b. The limits of integration for the outer integral would be a to b, and we'd let y go from c to d. The inner limits of integration would be c and d. But we don't have a rectangle. We've got a triangle. Here's what you do. The outer limits of integration for x in this case are still constants. For this triangle, x goes from 0 to w. W is a constant when I'm thinking about doing this calculation. When I think about doing the calculation, I'm thinking of w as a constant. After I finish the calculation, then I think of w as a variable, right? It's all in your head. It's all the perspective that you have. However, y does not go from 0 to w. What does it go from? Here's how you think about it. For any given value of x between 0 and w, I'll pretend it's right there, say, y goes from the second coordinate of this point up to the second coordinate of that point. The second coordinate of the lower point there is easy. It's just 0, right? 0. The second coordinate of this point up there depends on x. It's w minus x, in fact. This upper limit of this integral is w minus x. Okay, here's where we use independence. Independence allows us to write the joint density as the product of the regular densities of x and y individually. You could call them marginal densities. And that's a good thing. It's going to allow us to do something we wouldn't be able to do otherwise. Right? That's independence. That's the definition of independence in chapter 5. The joint density is the product of the marginal densities, and the marginal densities are the same as the ordinary PDFs of x and y individually. Okay, without making that assumption, it makes this harder. You really can't go much beyond that point. But because we can write this, here's the key. Here's one key. Double integral like this, there's really an inner integral and an outer integral. Don't always put parentheses there, but that's what's really going on. Sometimes called an iterated integral. There's a first integral, an inner one, and a second one, an outer one. For the inner one, the variable is y. I'm integrating with respect to y. Fx of x doesn't depend on y. It's constant, with respect to y. Therefore, it can be factored out of the integral. The inner integral, at least, not the outer integral, like this. I'll continue using parentheses. With respect to that inner integral, the marginal density of x is a constant. It can be factored out. Okay, is that really so helpful? It is actually, because now this inner integral can be simplified, can be in fact written without an integral sign. How? Think about it here. I'm integrating the PDF of y there. If I knew its antiderivative or an antiderivative, I could do that integral. Hey, I know an antiderivative, at least in the abstract, it's capital F. Subcapital Y. Think fundamental theorem of calculus, plug in the top limit of integration, subtract what you get when you plug in the bottom limit of integration. So that inner integral can be written without an integral sign. And in fact, it could even be simplified further. Does anybody see how? Could simplify that right there. What does that equal? What I'm pointing at? These random variables are non-negative. It's 0. Because x and y are non-negative. So they can't take on negative values with any positive probability. The CDF has a value of 0 at 0. Okay, so this is nice, I guess. Careful about writing the correct letters in all the correct spots here. That's the trickiest part. Okay, so what have we done? We've shown that we can write the CDF of capital W, which is x plus y, as a single integral, not a double integral, of this product. What am I after? I'm after the PDF of W. I need to differentiate this. Little f subcapital W is the derivative of capital F. In other words, I need to differentiate this integral. That sounds kind of familiar, or it should at least. Where the variable is in the upper limit of the integral, that sounds like a fundamental theorem of calculus, part 2 problem, right? Except there's a fly in the ointment here. That's not the only place W appears. It also appears right there. So what does that mean? That means we can't use the fundamental theorem of calculus to do this derivative. However, there is another rule that we can use. You probably never heard of it before. In fact, it's not something that I think about much. It's called Leibniz's rule, Leibniz integral rule. You could say it's a generalization of the fundamental theorem of calculus. It tells you how to find the derivative with respect to x of an integral like this, where x appears here, here, and here, which is essentially what the situation we're in, except with a w instead of an x. The t here is playing the role that the x does for us. I want to compare these things here. Compare this with this. For our problem in purple up here, w is playing the role of x down here, and x up here is playing the role of t down here. The rule says to do all that. Yeah, doesn't look so pleasant. Well, maybe I'll make this as an exercise for homework due Thursday. I'll leave it to you to check that these first two terms in our situation at least are 0. These first two terms. I think I'm officially making that a homework problem right now. This abstract setting for our problem, our situation, I want you to check that these first two terms are 0. And so we're left with just this thing over here. This Leibniz's integral rule says the answer is going to be the integral from 0 to w, because for us, the a of x is really an a of w, which is 0, and the b of x is really a b of w, which is just w, times the derivative with respect to not x, but w of this thing. It's a partial derivative symbol because there's two variables in here, an x and a w. However, the w only appears in the second factor there. This first factor is a constant with respect to w. Differentiated with respect to w, it stays as is. So we really just end up differentiating capital F. And that, of course, is little f. And that thing right there, that's the convolution formula in this situation. It is the PDF of capital W. And I could also write it as F sub X star F sub Y of W. And again, in this spot right here, we use the Leibniz integral rule. Okay. I'm not going to prove the Leibniz integral rule. Okay, that's beyond the scope of what we're doing here. We're just using it. And again, I'll leave it as an exercise due Thursday. I'll put it on Moodle to confirm that in our situation, these first two terms are 0. Question?
Does it not matter that it's a little f in Leibniz integral rule if we're using it as a big F at first?
The little f down here in the Leibniz integral rule, up in our situation, that's really represented by the product of little f sub x and capital F sub y, is the product of those two things is what the little f down here is. So the notation is, not the same, but it's the idea that's important. What is the function you're integrating? That's the key. Okay, so Leibniz integral rule, you probably never heard of that before this point. I think I learned about it in my multivariable calculus class, but I've never taught it when I've taught multivariable calculus. And before Jed Yang started teaching it, I've taught multivariable calculus plenty of times, but I never taught it because it's not really commonly used. Here's the main situation where I know it's used. Okay. This convolution formula is a good thing. It does make calculations simpler. Let's go back to our example before spring break, where we're looking at the sum of two exponential random variables that were also independent. So x and y are going to be exponential with parameter beta. And remember, beta is the mean of that exponential. And they're going to be independent. Question is, what is the distribution of x plus y? What we saw before spring break is that this turns out to be gamma parameters alpha and beta where alpha was 2. Remember that? We derived that before spring break in 2 ways. One with moment generating functions and the fingerprint theorem, which is the easier way to do it, and one with a double integral, which was the harder way to do it. And I got them in the Mathematica notebooks, the details, and I'll briefly show them to you, but we're not going to actually go through it. Confirming this with convolution formula is another way to do it. And it's easier than the double integral method, though I'm not sure if it's easier than the not necessarily easier than the moment generating function method. So how to do that? Do that. Confirm with convolution formula is what we're trying to do here. And by the way, of course, exponential random variables are non-negative. So we can use this formula. I can use the convolution symbol, the star symbol, if I like. And the formula from the previous page is that I do the integral from 0 to w of little f sub x evaluated at x times little f sub y evaluated not at x or y, but instead at w minus x. Integrate with respect to x. And this turns out to be an easy integral to do. What's the PDF of x? It would be 1 over beta e to the negative x over beta, right? There's an exponential PDF with parameter beta if I call the variable x. PDF of y, if the variable was called y, would be 1 over beta e to the negative y over beta. It's the same PDF, really, just a different variable name. But I'm replacing y with w minus x here. That's an x there. Can't quite see that. That's an x. Of course, I can distribute the minus sign through. That's the same as e to the negative, e to the positive x minus w over beta. And I could write that using properties of exponents like this. And then continuing to use properties of exponents, if I combine these two things, I get e to the 0, which is 1. So I'm really integrating 1 over beta squared. There's 2 factors of 1 over beta. E to the negative w over beta dx, not dw. This is a constant with respect to x. Very easy integral to do. Get 1 over beta squared e to the negative w over beta times x. X goes from 0 to w. And when you simplify that, that's 1 over beta squared. Replace x with w. I'll put it in the front. W e to the negative w over beta. And that is the PDF of a gamma. PDF of gamma when alpha is 2 and beta is beta. All this is assuming w is greater than or equal to 0. That is definitely easier to do than the double integral method, where we did a double integral to find the CD. There was the CDF method computed with a double integral. We did the double integral. Then we had to differentiate the double integral to get the final answer. I'll show you the details, though I won't go through them step by step. This is quicker using the convolution formula, but you gotta know the convolution formula. Ready for me to show you the details? Again, we're not going to go through them step by step. So here, okay, I've got a number of things in this notebook. And again, I'll share this notebook. Somebody could remind me to share the notebook because I often forget. So here's the derivation I just did with the convolution formula. With moment generating functions, the computational details in Mathematica are here. I'm not going to enter this code. Here was the double integral method. This is what we did before spring break. Did that double integral. Got this for the CDF. Then we differentiated to find the PDF. Got the same answer. Okay, so once you got the convolution formula, it is easier. So I'm probably going to assign another homework problem where you're going to use the convolution formula. It's a second homework problem to do in a different situation. Can I clarify anything? Not saying this is easy to understand. Just trying to make use of it. And it is good to see the CDF method coming into play again. We are trusting this Leibniz integral rule to get this answer. Convolution is a useful thing. All right, what should we do next? I would like to use Mathematica for a fair amount here. So my next goal is to do one more problem. This is the final problem we'll do. I'll probably give you a homework problem similar to this, where we're going to add two random variables. But this time we're going to make it harder on ourselves. Wait, isn't this already hard enough? We're going to make it harder on ourselves by making these random variables not independent. So we will not be able to use the convolution formula. We'll have to do a double integral. And we'll not be able to use independence to simplify that double integral. We'll just have to do it as it is. Okay. This will bring up a question, when would you use a situation with non-independent random variables? I'll maybe talk about that a little bit on Thursday. Before we do that, maybe we should look at using Mathematica to confirm things here, because we're going to use Mathematica further on down, so it might be good to review that. So here I was using Mathematica in various ways. For example, to remind myself of the PDF of an exponential. That's code that will tell you what the PDF of an exponential is right there. PDF exponential distribution. Do note that in Mathematica, you have to plug in 1 over beta as the parameter instead of beta itself. 1 over beta is often called lambda, and it's related to Poisson random variables. And if you remember, Poissons and exponentials are related. I have talked about that. If the Poisson is like the count of cars that come into an intersection during an hour, if the parameter is lambda for the average number of cars that come in an hour, 1 over lambda is the beta for an exponential that gives you the wait time between cars coming into the intersection. If that went over your head, don't worry about it, but that's something to keep in mind. Just reminding you, you can use random variate to generate data. So this is going to generate data from 2 exponential distributions. And if I do it separately like this, x data and then y data, effectively they are independent simulation-wise. The results of one of these is not going to be affected by the results of the other. I've entered them. What's the x data? I could do this and see them all 10,000 numbers. 10,000 numbers there. Of course, the semicolon will suppress outputs, so I don't have to see the numbers. Mean of an exponential distribution is beta. In this case, 1 over beta is 0.1, so beta is 10. We should expect a mean of 10, close to 10 for both the x data and y data. Standard deviation for exponentials also equal beta. Variance is beta squared. So these numbers are all close to 10, not exactly 10 because of simulation. You can make histograms, and you can see by if you plot the PDFs of these things, well, not the PDFs themselves exactly, but scaled up versions, 20,000 times the PDF. You can see, especially with 10,000 data points, we got a pretty good match. W data, that's where I'm adding the X data and the Y data. W is X plus Y. I'm not doing that with random varied, but I'm doing it with table because I'm wanting to take the actual X data and Y data that I got, although because I use colon equals, it'll probably redo it, and compute W data for the sum. It takes a little longer. And here I computed the mean and standard deviation. Notice 20. Hey, 10 plus 10. The mean of X and the mean of Y are both 10. 10 plus 10 is 20. That's very close to 20. 14.2, what's that close to? How about square root of 200? Is what it's close to. 100 plus 100. Remember, the variance, 10 squared, is 100. And if you make a histogram and plot also, notice this is 20,000 times the PDF of W. Notice the extra factor of W in there. That's a gamma with alpha equal to 2. It's not an exponential distribution, but it does follow. The simulated data does follow the shape of the PDF for a gamma distribution with alpha equal to 2 and beta equal to 10. The 0.01 here, by the way, is 1 over beta squared, which is part of the formula that we did get. 1 over beta squared.